Picture this. You're standing inside the combustion chamber of a massive, resting commercial jet engine. It's completely quiet. If you were to strike a match and spray aviation fuel onto the metal walls, the engine wouldn't start. You just get a destructive fire that would warp the turbine blades and melt the outer casing. A jet engine simply cannot start itself. Unlike a car engine, which can fire its cylinders from a complete stop using a small battery, a gas turbine needs a massive, continuous rush of high-pressure air just to sustain combustion. But here's the catch. That air is compressed by the engine's own compressor, which is spun by the turbine, which is powered by the combustion itself. It's the ultimate chicken and egg problem. To start the engine, you must already have it running. Breaking into this closed loop takes an incredible amount of brute force. To start a modern turbofan engine, like the ones hanging under the wings of a Boeing 777 or an Airbus A350, we have to spin a central shaft assembly that weighs more than 4,000 kilograms. This high-pressure rotor has to reach roughly 2,500 revolutions per minute before it can compress enough air to support ignition. At that speed, the compressor is swallowing and compressing more than 50 kilograms of air every single second. To get it there, the starting system has to dump more than 300 kilowatts of mechanical power directly into the core. How we deliver that kind of muscle, using a device small enough to fit inside a tight engine cowling, is a masterclass in mechanical engineering. First, we have to understand that the starter doesn't even try to spin the entire engine. That would require far too much energy. A modern turbofan is actually split into independent, concentric shafts that spin inside one another. The outer spool, which engineers call N1, connects the giant front fan you see from the gate to the low-pressure turbine at the very back. The inner spool, N2, connects the high-pressure compressor to the high-pressure turbine. The starter only engages this inner N2 spool. Spinning that massive front fan from a dead stop would take an absurd amount of torque. So, the starter leaves the fan alone and spins only the high-pressure core. As this core spins up and begins drawing air through the engine, the passing air gently coaxes the front fan to start windmilling on its own. It only truly screams to life once combustion begins. In the early days of aviation, engineers had to get creative, and their solutions were often pretty wild. Some military jets relied on cartridge starters. These were essentially blank cartridges packed with solid gunpowder, loaded directly into a breech on the engine. When the pilot pressed the start button, the cartridge fired, and the hot, expanding gas blasted through a small starter turbine to spin the engine core. It worked great for quick combat scrambles, but cartridge starts were violent. They coughed out thick black smoke, slammed the delicate turbine shafts with massive shock loads, and left behind corrosive soot. Not to mention, it meant air bases had to stockpile explosives. Electric starters were another option, but they ran into a hard wall when engines grew larger. To start a modern commercial turbofan electrically, you'd need a motor and battery banks so heavy the plane would struggle to get off the ground. All that dead weight would ruin the airplane's efficiency on every single flight. The real breakthrough happened when engineers stopped trying to use heavy electric motors or dangerous explosives and looked at the one thing the airplane already had in abundance: air. Instead of using electricity to turn the engine, modern airliners use a pneumatic start system. Air does the work. The heart of this system is the air turbine starter, a remarkably compact tool that turns the energy of high-pressure air into raw rotational torque. This air, which we call bleed air, is delivered at a pressure of about 3 bar, or 45 pounds per square inch, and a temperature of nearly 200 degrees Celsius. It's hot, fast, and incredibly dense. Because air is light and can be easily guided through insulated pipes, the heavy machinery that actually compresses the air doesn't need to be on the engine at all. It can live somewhere else entirely. So, where does this high-pressure air come from? On a typical flight, it comes from one of 3 places. The The most common source is the Auxiliary Power Unit, or APU. This is a small, self-contained gas turbine tucked away inside the very tail cone of the airplane. When you're sitting at the gate and the main engines are off, the APU runs in the background, keeping the lights on and providing bleed air for the cabin air conditioning and engine starts. But if the APU is broken, the ground crew can hook up a mobile compressor cart on the tarmac, often called a Huffer cart. This cart pumps high-pressure air directly into a port under the fuselage. Finally, if one main engine is already running, pilots can open a cross-bleed valve, stealing some of the compressed air from that running engine to spin the starter on the other side. The source changes, but the goal is always the same. No matter where the air comes from, it gets routed through heavy-duty plumbing to a starter control valve. This is essentially a high-pressure butterfly valve that regulates the flow of air into the air turbine starter. The starter itself is tiny. It weighs less than 20 kilograms, but it generates hundreds of horsepower. Inside its housing, the incoming air rushes through stationary stator vanes that guide it onto a small turbine wheel. This wheel spins at a blinding speed of over 60,000 revolutions per minute. To turn this high-speed, low-torque rotation into the slow, high-torque force the engine needs, the starter uses a set of planetary reduction gears. This gear system drives an output shaft connected to the accessory gearbox. The accessory gearbox is a metal housing bolted to the bottom or side of the engine casing. It contains a train of gears that drive everything the engine needs to run, like fuel pumps, oil pumps, and electrical generators. But the starter needs to spin the high-pressure spool, which is suspended right in the dead center of the engine core, far out of reach. To bridge this physical gap, engineers use a radial drive shaft called a tower shaft. This is a solid metal shaft that runs vertically through one of the hollow struts in the engine's main intake frame. It connects the gears in the accessory gearbox to a bevel gear mounted directly on the high-pressure compressor shaft. When the starter turns the gearbox, the tower shaft spins, rotating the core of the engine from the inside out. Slowly, the giant rotor starts to roll. As the N2 shaft speeds up, the compressor blades start pulling air into the engine, squeezing it, and pushing it back toward the combustion chamber. When the rotor hits about 20% of its maximum speed, the engine's main computer, the FADAC, decides it's time. It commands the fuel control unit to open the valves, spraying a fine mist of aviation fuel into the chamber. At the exact same moment, the igniters spark. These aren't like the spark plugs in your car, which produce a tiny, continuous spark. A jet engine's igniters are high-energy devices designed to blast out a rapid series of intense electrical arcs. Each discharge releases up to 20 joules of energy. That's enough to rip through the high-speed air and ignite the fuel mist. The fire is lit. With ignition established, the temperature inside the combustion chamber shoots up, and the expanding exhaust gases blast backward through the high-pressure turbine. This turbine absorbs energy from the hot gas, using it to spin the compressor even faster. Now, the engine is accelerating under two forces: the pneumatic push from the starter and the thermal power of its own combustion. Within a few seconds, the engine crosses a critical threshold: self-sustaining speed. This is the point where the turbine is producing enough power to keep the compressor spinning without any help from the starter. From here, the engine can accelerate on its own. Now, we have to disconnect the starter, and we have to do it immediately. If you want to understand not just what flies over your head, but why it's built that way, subscribe to Flight Simplified and stay with me. If the starter stayed mechanically locked to the engine, the results would be catastrophic. As the engine climbs to its idle speed of over 12,000 revolutions per minute, it would spin the starter turbine wheel up to an impossible 300,000 revolutions per minute. The starter would literally explode, throwing shrapnel through the engine casing. To prevent this, the gearbox uses a Sprag clutch. This is a one-way mechanical clutch that only transmits torque from the starter to the engine, never the other way around. It features an inner race connected to the starter, an outer race connected to the engine, and a set of asymmetrical, kidney-shaped cams or sprags sitting in between. When the starter turns, the sprags tilt and lock the two races together. But the moment the engine fires up and spins faster than the starter, the outer race overruns the inner race. The sprags tilt back, releasing their grip instantly. There are no electronics, no sensors, and no delays. As the engine speeds up, centrifugal force pulls the sprags completely clear of the inner shaft, preventing any friction or wear during the flight. The starter comes to a quiet halt while the engine screams right past it. Even with the starter safely disconnected, the engine isn't out of the woods yet. It still has to get through a delicate aerodynamic hurdle. A jet engine's compressor is designed for cruise flight, compressing massive amounts of thin, cold air at near supersonic speeds high in the sky. But during a ground start, the compressor is spinning slowly in thick, warm, stagnant air at sea level. In these conditions, the angle at which the air hits the compressor blades is far too steep. The airflow can stall, breaking away from the blades and creating turbulent pockets. If this stall spreads, the air stops flowing front to back. Instead, the high pressure in the combustor forces roaring hot gases to blow backward through the compressor and out the front intake. This is called a compressor surge, and it can destroy an engine in a heartbeat. It's an absolute aerodynamic emergency. To keep this from happening, the engine has to actively change its own internal shape. Modern turbofans do this using variable stator vanes. These are stationary guide blades inside the compressor that can rotate on their individual axes. During the start sequence, the FADAC uses fuel pressure to turn these blades, closing them down to guide the air more smoothly. This reduces the angle of attack, keeping the airflow attached to the spinning compressor blades even at low speeds. At the same time, the FADAC opens transient bleed valves along the sides of the compressor. These valves dump excess air directly into the bypass duct, relieving pressure buildup and keeping the air moving in the right direction until the engine stabilizes at its idle speed. The engine literally morphs its internal geometry in real time. Once the engine settles at ground idle, usually around 60% of its high-pressure spool speed, the start sequence is officially over. The starter valve closes, the bleed air cuts off, and the air turbine starter goes quiet. Inside the gearbox, the Sprag clutch spins freely, completely disconnected. The engine is now a self-contained, self-sustaining powerhouse. It is drawing in its own air, compressing it, burning fuel, and producing the power needed for flight. The classic loop has been broken. What started as a simple gust of air from the tail of the plane has successfully transitioned into a self-tuning, high-speed thermal cycle. The mechanical paradox is resolved. Out on the tarmac, the ground crew disconnects the heavy starter hose and moves away. Under the wing, the giant turbofan hums with a low, powerful roar. Its titanium fan blades spin in a smooth silver blur, creating a shimmering wave of heat haze that warps the view of the runway behind it. Until next time.